Michael Faraday is one of my science nerd heroes. I always have to go on a gentle rant about him. He lived in the 19th century, 1800s. I think he died in 1890 or so. He was a very, very poor young lad, but Faraday is considered to be the greatest experimentalist in history. His math skills were terrible. In fact, he was famous for writing his conclusions in English because he didn't know how to do variables or formulas. But Grant, if you needed to come up with an experiment that would eliminate 9 other variables and only target the one thing you were wondering about, he was the best at it. Maybe the best in history. He actually grew up as a bookbinder. He worked for his uncle. He had very little educational training, but he was fascinated by science. The story goes when he was, and I think I've told you this, 5 years old. Psst, I'm telling a story. You guys can be quiet. Thank you. When he was 5 years old, his uncle gave him a compass, and he saw that the needle moved. And he did a very intelligent thing. He climbed into his bed, he pulled the covers over his head, and the needle still moved underneath the blanket, and that scared him, Rachel, because that meant whatever was moving the needle was underneath the blanket with him. Which for a 5-year-old to think is that he was already thinking about fields. All of our field theory comes from his ideas. This idea of invisible fields going out in all directions, like the invisible tentacles of an octopus. When he was about 14 years old, Emma, he went to a free science talk. At that time, only wealthy people got educated. But the wealthy people often would do public lectures, and so Sir Humphrey Davy did a free talk doing lots of stuff with chemistry, lots of stuff with the current understanding of electricity, lots of science demos, and they were very, very popular. Well, Faraday went, and he took very meticulous, very copious, very well-done notes. And because he was a bookbinder, he bound them into a book and he sent them to Sir Humphrey Davy. Sir Humphrey Davy saw this and hired Faraday as his lab assistant. Maybe the best hire in history. Because it very quickly became obvious Faraday was brilliant. He had an intuitive understanding about things and a very, Vanessa, weird way of thinking about things, which helped him be brilliant. He didn't just accept the status quo. He had to build an experiment and prove it to himself. Eventually, he invented the electric motor and the electric generator. He was so famous that when he died, Queen Victoria offered him burial in Westminster Abbey, where Newton is buried, where the knights are buried, and he turned it down. He was a very religious, humble man. Nah, no thank you. Turned down his knighthood, turned down, I don't need that. So there's my Faraday rant. Worth reading a bio on him, he's pretty cool. In the previous unit, Emma, we learned that when charges move current, they produce a magnetic field. Moving charges produce a magnetic field, whether it's a little individual charge or we lock them in a wire. In addition, we also learned that an external magnetic field will exert a force on a moving charge, whether it's a curve turning it into a circle, like a particle accelerometer, or on a wire, getting it to completely move, which led to the electric motor. Early in the 19th century, scientists such as Michael Faraday and Joseph Henry were aware of these, and they asked the obvious question. They said, look, if a current produces magnetism, might magnetism produce current? Can we create electricity without chemical batteries? Yeah! We need to do some terminology. Recall, electromotive force, or EMF, symbol E, is an archaic word, and it refers not to a force, but to voltage, to the voltage of a cell. So V, voltage with the wings, and EMF, E, mean the same thing, and they're going to be used interchangeably, and in particular, it is traditional to use that for voltage in this unit, partly in Faraday's honor, because it's what he used, and he's one of our nerd heroes. If a piece of wire moves through a magnetic field, like in the picture. Now, in this picture, the magnetic field is into the page, so if you want to, you could put some X's there just to remind you that's the symbol for into the page. And we're going to focus on just one charge. I'm going to zoom in. All of you right now, put a little proton right there, right in the middle. Now, understand, Vanessa, there's, I was going to say trillions of protons, actually probably dodecadillions of protons in that metal wire. But we're just going to look at one. What we're doing is we've got a string or a rope or something. We're pulling it this way. And I don't care what's pulling it, some external force. So it has a velocity down the page. Which way is that proton moving then? down the page. All of you point your thumbs down the page. Which way is the magnetic field? Into the page. So point your fingers into the page. So if you're using my board, your hand would look like this. If you're using your paper, I think your hand would look like that, right? Here's what I notice. Which way is the proton going to get pushed? To the right side of the wire. Which way are the electrons going to get pushed? To the? What will happen is we will get negative charges over here, positive charges over here. What you've just done is you've separated charges. That's a voltage. That's a voltage. You have induced a voltage from motion. You have done work on the rod separating charges. Some of the energy that you were using to pull it went into separating charges. In fact, you would physically feel a resistance to you pulling it, and it would be the physical effort it was taking to separate those charges. Okay? You guys with me? Yeah? Okay. Let's get back here then. Since the charges have been separated, which takes work, we have voltage, because voltage is defined as potential energy or work per coulomb. We call this voltage induced voltage, motion voltage, since the energy in this case comes not from chemicals like in a Duracell battery, but from motion. McKinley, now all we're going to do is be clever for the next few days, and this is going to lead us to the electric generator, the ability to use something turning, that's also motion, to create current. In other words, motion can induce an EMF, a voltage. Find an expression. Okay, well, the definition of voltage was potential energy per coulomb. And really that potential energy came from work done on moving the charges. So I'm going to say, by the way, I'm going to start using our archaic symbol for voltage because that's how it appears on your formula sheet. I'm going to say it's force times distance over Q. Which force? Magnetic force. Magnetic force. So the magnetic force on a wire is QVB. Sorry, I said that wrong. Magnetic force on a proton is QVB. I know there's a bunch of protons in that wire, but we're just looking at one. Okay? And then the distance would drop down. We have a Q still on the bottom. So Jake, that was that thing right there from last unit. Hey, what do you notice? What happens to the Q's? That's convenient. Now this D here is really the L length of the wire. And this gives us our first equation. You want to know how many volts you're inducing by moving a wire through a magnetic field? The EMF is given by BLV. See the B, see the V, and then instead of D, I used L for length of wire. Except also, these all have to be at boom, 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 right angles to each other for my right-hand rule to work. It's a scalar equation, because voltage is a scalar. B is the external field, the magnetic field, which, Vanessa, we just learned how to create magnetic fields from solenoids. B was mu naught Ni over L. So I have complete control over that variable. You want a stronger magnetic field? Wrap some more wires around it or bump up the current. L is the length of wire that you're moving, and V is how fast. So you want a bigger voltage, longer wire, move it faster, or bigger magnetic field. And we're going to get even better than that. Okay? Again, perpendicular, key idea, you only get volts when all three are perpendicular, and I'll show you why. If the wire and the speed are not perpendicular, we only get a small amount of voltage. What if I move the wire this way? So instead of moving the wire like this, perpendicularly to the motion, what if I have the wire and the motion parallel? Well, again, let's focus on a little positive charge right there. Magnetic field is still into the page. Which way will that positive charge feel a force? Point your thumbs down the page. Magnetic field into the page. It will feel a force to the right. Here's the problem. Can it travel very far to the right in that direction? You really are not going to separate the charges very much in this thin wire. Okay, fine. You'll get, don't write this down, a few extra positives there and a few extra. You're not going to do much work separating charges, Ryan. You're not going to generate much of a voltage. Is that okay? So, you can make a little note here. Nowhere for the separated charges to go. So, little EMF created. I wonder if I have the symbol for that little funky voltage thing. That would be cool. I probably do somewhere. I'll have to go find it. I can't say no EMF because it is true that in that thin wire there would be a tiny bit of separation. Yeah, it's close enough to 0. All right. So example 4. Here's our first question. It says, find the voltage induced, the induced EMF, across the ends of the moving wire and indicate which side is positive, which side is negative. Let's double check. The wire goes this way. The magnetic field is this way. What direction is the velocity in this question? You have to kind of look carefully. Into the page, that's that X. So they are all three at right angles. We are going to get an induced EMF. Double check that. Now on your test, I won't try and trick you. But in your homework, I would have no problem giving you a question where there is very little EMF because they're not all at right angles. This is an induced voltage in a wire. It's going to be BLV. This part is plug and chug. How big is the magnetic field? Big. Very big. How long is the wire? 0.8. How fast is it moving? 5.25. How many volts will we create? Induce from motion. What do you get? 5.25? Hey, that's almost, that's like a few of these. That's not bad. That's approaching a chemical battery. 5.25 volts. Which end of the wire will be positive? Okay. Now, here's our individual proton right there. We point our right thumb in the direction that it's moving. Which way is it moving? What? Into the page. That's the velocity. So you should be pointing your thumbs down at your paper. We extend our fingers like we're high-fiving in the direction of the magnetic field. I'll do it up here. I would go boom, boom. Oh, which side of this wire is going to be positive? The left side. The right side will be negative. By the way, we don't generate voltage this way, but this was Faraday's first thinking. We're eventually, Marissa, going to reach the point where we're going to say, hey, what if we have a coil of wires and we spin them? Which is why all generators do that. Okay? But one of the applications, back when we used to have smoking on flights, and every seat was equipped with a little cigarette lighter that you pushed in, and then it would pop out all hot. They would actually get that EMF by treating the plane like a rod. So find the motion induced across the wings of a plane. So the magnetic field, we're going to assume that the magnetic field is into the page, into the earth. We're going to assume that the plane is flying up high enough, which it is, that the magnetic field has already started to curve back down to the ground. Okay, you've seen the pictures probably somewhere what the Earth's magnetic field curving. So how many volts will you induce? Well, the induced EMF is going to be BLV. Which magnetic field? 0.008. Uh-oh. Which length? They gave me two. The length that is perpendicular to the direction of travel. So which length am I going to use? The 150 or the 60? The 60. Which velocity? 320. How many volts will you generate across the body and wings of this airplane, which is made of metal? 154 volts? That's more than it's coming out of your plugs. My understanding is they used to run the cigarette lighters off that. I don't know if they still use this voltage. Now, again, that's not free energy. That energy is because remember, voltage is energy per coulomb. That's coming out of the fuel. It's lowering your gas mileage. Nothing's free, but it was a neat application. I don't know if they still use it to power any of the electronic devices in the backs of the seats or not. Oh, come on, that's pretty cool. No? Okay. Let's get even more interesting. What if instead we connect the moving metal strip to conducting rails? We slide it along some wires. So now we have a complete closed loop. Now we're going to have current flow. Instead of just separating the charges, now they'll have somewhere to go because now they're connected to metal on either end. Example 6 says, show that the polarity of the moving strip below on the left, oh, that's too big. Show that this is like a battery. Okay, you ready? Here's our little proton right there. Which way is this proton moving? To the, point your thumbs to the right. Which way is the magnetic field? What does the question say? Region of field is what? Okay, so to the right, out of the page, which way will the proton get pushed? And that's going to be the direction of the current. You're going to have the current going this way. Why is it current now instead of voltage? Because Ty, when the positives gather here, oh, now they can flow down there because I've made a little metal wire touching it. And I put a resistor so we weren't short-circuiting. This could be a little bulb. We could light a light bulb now. The current would flow like this. The current would flow like this. Mathematically, Rachel, that's the same as having this circuit where you have a battery with the positive end going that way. They are mathematically equivalent, physics equivalent. Now we're going. Now we're talking. Oh, it gets better. It gets better. Even cooler. If there is a current flow moving the metal strip or wire, then there is also a magnetic force on the wire that tends to slow it down. Say what? Again, let's zoom in. Here's our picture. Now, this velocity here is coming from someone pulling it, or a machine, or whatever. That's an external force, okay? So the proton already was moving to the right. However, as soon as we add current, not only is that proton moving to the right, it's also moving down, right? Point your thumbs down the page. Magnetic field out of the page. Which way will this bar feel a force? Which way is your palm? So if I go down the page, out of the page, you know what? My palm is pointing in the opposite direction that we're pulling. You will physically feel something slowing you down. This is magnetic braking, which you may have read about or heard about. There is going to be a magnetic force that way. I've been looking like crazy for, I had last year and for a few years a crank generator flashlight. Any of you seen those flashlights that you turn the crank on? I've lost it. I'm going to buy one on the weekend. Have you ever used one? That force that you feel when you're turning it is not because it's a lousy engine that has lots of friction. It's almost frictionless. What you're feeling when you try and crank it, you're physically feeling that force there resisting the direction that you want to move it, because you've started to create a current, but now it's also moving that way. There's a net force backwards. Or in other words, Justice, you get nothing for free. The universe still says to you, I'm sorry, there's no such thing as free energy. See, otherwise, we could simply set this up so that instead of having some machine pulling it, we could have it sliding downhill and just get like free from gravity. No, it's going to slow down. But that's also kind of cool. Magnetic braking. Next page. So let's put it all together. The strip below is 12 centimeters long, 0.12 meters. It's moving at 4.7 meters per second. The external magnetic field is 0.08 Teslas, out of the page. The resistance of this rail circuit is 0.025 ohms. A says, find the induced or motion voltage. Okay. Here's our proton. Again, there's several trillion of them, but we'll just look at one. And again, I should point out, Atla, in real life, the protons don't move. They're locked in the nucleus. It's the electron moving. But hopefully I have convinced you that it's much nicer to think about protons moving. Everything makes much more sense. Curse you, Ben Franklin! Anyways, okay. Which way is the proton moving? To the right. Magnetic field out of the page. The proton is going to feel... Okay, so the current is going to be clockwise. Now, as soon as that happens, not only is that proton moving to the right, it's also moving down. We'll tackle that in a second. First thing it wants is the induced induced motion voltage is BLV, as long as they're all at right angles to each other, and they are. What's the magnetic field? 0.08. What's the length? 0.12. What's the speed? 4.7. How many volts are we inducing? .08 times 0.12 times 4.7. 0.04512. Is that right? So I'll go 0.045, but I'll keep this on my calculator. Not much. Units. Voltage. Yeah, volts. B. What do they want me to find? What did I find in part A? It'd be nice if I had an equation that had current and oh! Right? Current was V over R, where the voltage is 0.045. Hey, please tell me, did they give me the resistance of this circuit? They did? Oh, cool. How many amps of current will be going through here? Divided by 0.025. Oh, 1.804, all right, 1.8 amps. That's a fairly big current. That would give you a nasty jolt. Okay. Kyle, what does part C want me to find? Magnetic force, FB, on the what? Not on a moving charge, but on a strip. You know what? That was Bill. Do I know B, the magnetic field strength? Yep. Do I know I, the current? That's what I found in part B. Do I know the length of wire? Oh, now it's plug and chug. 0.08. 1.8. 0.12. 0.017 newtons? Is that right? Or no? Yes? 0.017 newtons. All right. Now, let's do some thinking. Suppose I pulled this faster. If V got bigger, what would happen to the induced voltage? Bigger. What would happen to the current? Bigger. What would happen to the force resisting me? The faster you pull, the harder you pull, the harder nature pulls back and says, "Oh no, you don't." This is also this is also a consequence of the law of conservation of energy. You get nothing for free. You get nothing for free. So then Faraday said his next experiment was, all right, what if instead of moving a straight wire, what if I move a coil, a loop, a solenoid, but we'll just do a single loop of wire? What will happen then? He thought, this is going to be kind of cool. This is going to be great. So I'll zoom in. Well, first of all, I'm going to treat this as 1, 2, 3, 4 separate wires. And I want you to notice the top and bottom wire are moving in the same direction as the velocity. I think you're going to get no voltage there and no voltage there. Right? We already demonstrated that a couple of questions ago. So let's look at a proton right here. Which way is it moving in this coil? Well, which way is the coil moving? Point your thumbs to the right, please. By the way, Vanessa, did I say we were going to be using the right-hand rule quite a bit in the next few days? You're going to get good at it, trust me. Which way is the magnetic field, Vanessa? So I would be going to the right and out of the page. Which way on the back side there, which way will that proton feel a force? So it's going to go that way. Let's look at the front chunk of wire. Here's a proton. Which way is it traveling? To the right. Which way is the magnetic field? You know what? It's going to feel a force that way. You have two voltages that are going to meet like the, you know what? What's the net EMF here? 0. Doesn't work. Doesn't work. Okay? The net EMF is 0. It says explain your answer using relevant you know what? Right-hand rule. There's your answer. That's my usual abbreviation for right-hand rule, RHR. Okay? In fact, this goes back to way back last unit when we had two batteries facing each other and they said they'll cancel each other. Essentially, you've done the same thing. You've got two opposing voltages. You're going up one chairlift, down the other chairlift. You're not gaining any height. We're going to come back to that coil idea, though. It's too good to let go. But then he said, okay, if pulling this wire, if supplying a velocity gives me a current, will supplying a current give me a velocity? And here is your rail gun. Here is your roller coasters that launch from ground level really fast. So in this circuit, the wire strip is initially at rest. I bet you that's important. And there is a power supply. There's a battery. It says, first of all, for the circuit below, find the induced voltage. What's the direction of the current? What's the direction of the magnetic force? What happens to the strip? Okay, here we have a battery. You know what? The current is this, is it not? Yes? So the direction of the current is counter-clockwise, or you could just do that. I skipped part A. Alex, what does part A want me to find? Why can I say this? What was our equation? Induced voltage is equal to what? BLV. What's V? At the picture right now, it's 0. Okay? What's the direction of the magnetic force? Well, there is a proton right here. Which way is the current moving in that wire? Up the page. So which way are the protons moving in that wire? Up the page. Point your thumbs up the page. Magnetic field out of the page. What direction will this wire feel a force? This is it's going to start to accelerate. This is your rail gun. This is we're going to launch stuff using magnetic fields and currents. Okay? Right? To the right. F is that way. And it has to accelerate because there's an unbalanced force in that direction, Kyle. Newton's first. So what happens to the strip? It accelerates to the right. In fact, it starts to speed up. As soon as that happens, Ryan, we have situation example 11. Because now, not only, don't write this down, not only are the charges moving up the wire because of this battery, but which way is the wire itself moving? To the right. So now, this is what we're going to write down. Here's our proton. We already analyzed it moving up the page, but which way is it also moving? To the right. Magnetic field out of the page. Which way will the proton feel a force? Against the current. Resisting the current. Fighting against the battery that's speeding it up. Okay? So first of all, what happens to the induced voltage? Well, since the induced voltage is equal to BLV, the induced voltage does increase. What happens to the current? Well, because now you've got some current floating, pushing down, your net current decreases because although the battery is pushing stuff up the wire, the induced EMF voltage motion force is pushing charges down the wire. And since magnetic force is Bill, what happens to the force on the wire if the current gets smaller? What happens to your acceleration if the force gets smaller? F equals ma. If F, because m's not changing. You're still speeding up, but you're not speeding up as fast. And a few seconds later, you're still speeding up, but not speeding up as fast. In fact, eventually, you'll reach and what is that constant speed? When the voltage created by the motion is exactly equal to the voltage coming from the battery. When your net voltage is 0, it'll go at a constant speed. Isn't that cool? That's a railgun. You want to get it to go faster? Bump up the battery. So this is, for example, what apparently, according to the U.S., Saddam Hussein was trying to build in the first Gulf War, before you guys were born, in the early 90s. The U.S. stopped a ship that had these long metal tubes, and although it was claimed that they were being used for oil pipelines, the U.S. said, no, we think they're being used to make a rail gun to launch artillery a great distance. Oh, and if you make the artillery shell out of metal, it will be the conductor itself. Great. Okay. Says explain your answer using relevant physics principles. Sorry, Vanessa. You awake? Ah! Turn the page. You guys will miss that. There's only a few more days of it. So, what are some neat applications? It has been proposed as a way to launch spaceships from the ISS after docking. So in the ISS, we would first of all, we get our power from the sun, so we have a good-sized battery to begin with. In fact, I can make this a bit bigger. The spaceship itself would be the conducting rail. So if you draw with me, here's the current supplied by the International Space Station's solar cells. And there's a magnetic field right here. Which way is the magnetic field? into the page, and we can create that from a solenoid, which also we can get the power for from the solar cells. And we're going to use the spaceship itself as the conducting rail. So the proton right here, because of the battery, is getting pushed that way. Yes? The current is going like this. So which way are the protons moving in the space shuttle or in what other spacecraft we put on there? Down the page. Point your thumbs down the page. Magnetic field into the page. Which way will the space shuttle feel a force? And it will leave without having to fire its jets. We probably don't want it to fire its rockets close to the space station. Okay. That's a cool application. Again, the faster it moved, the less it would accelerate. So you would feel a big hoot right away and then less of an acceleration as you sped up. Okay. So that's one application. Another application is in electric motors. It turns out in an electric motor, as soon as the coil starts to move because of the battery, now not only is the current moving through the coil rectangularly, it's also spinning, and you're going to find, we'll look at this in a few days, you're going to generate what we call a back EMF. We're going to do an entire lesson on that. As this strip continues to speed up, albeit at a lesser rate, the induced voltage will continue to grow and grow and grow and grow. What happens when the induced voltage is equal to the supply voltage? Well, when the induced voltage is equal to the supply voltage, the net voltage is 0. And the net current is going to be V over R. What's the net current going to be? And so then, since the magnetic force is Bill, what does the force on the wire end up being? And if your net force is 0, what's the correct answer? A, B, C, or D? We're going to say that. Now, in real life, actually, because your force speeding it up is 0, it would begin to not slow. It might slow down just a tiny bit, but as soon as it slowed down just a tiny bit, now you would have the battery's voltage being like 0.001 bigger than the induced voltage, and that would give it a tiny nudge to keep the a tiny bit of a force. It'll kind of, and then it'll eventually settle at a constant speed. That will be the maximum speed for your railgun. That will be your max. Oh, explain your answer using relevant physics principles. There, right? That'll be, Alex, your maximum speed for your railgun. I wonder how fast that is. Can we calculate that? Okay. It's when the induced voltage, when that equals that. Okay? So let's see what happens here. We have the force on the wire is Bill. But what I really want to look at is the current, because that's going to be I think I'll be perfectly honest, right now I'm totally blanking on this question and I'm having to rederive it. I'm not going from memory, so we're going to see where we end up. I don't know why, but I'm having a complete brain cramp right now. Is that what I want, Mr. Dueck? I want it when those two are equal, So I've said this is I times R, but I'm using the EMF in place for the V, and I'm writing an expression for that. Is that right, Mr. Dueck? I need to think about this. And don't worry, I won't be asking you this question on a test, but you can calculate the maximum speed. I'll remember this in like 20 minutes and then, Let's try some applications with numbers. In each situation below, find the induced voltage, the net voltage, the net current and direction, and the magnetic force and direction. Hey, there's 2 questions. Why don't I do that? You know what? Let's do these at the same time. So the induced voltage is going to be BLV. What's the induced voltage in the left-hand situation? By the way, are you also seeing why I'm using the EMF symbol? Because otherwise I'd have, again, a V and a V in the same question. Like that wasn't confusing enough. So what can I say this? V is 0. The right side should be a bit more interesting. Looks like the magnetic field is 0.35 Teslas. The wire is, did they tell me how long the wire is? Oh, 4.1 meters in the picture. I had to look there. And the speed is 8. What's our induced voltage?
11.48.
Sorry?
11.48.
Is that right, folks? Okay. Now, by the way, that proton is moving to the right, magnetic field into the page. It is going to feel a force this way, which is going in the opposite direction that our source voltage is. So what does B want me to find? Net voltage? Is that what it asked for?
Yeah.
Yeah? Well, the net voltage here is still 320 volts. But the net voltage here is going to be the 320 source minus the 11.5, 310, 309, 308.5? Yeah. By the way, if this went faster, what would happen to your induced voltage? Bigger. What would happen to your net voltage? So the maximum speed is actually when this equals 320 volts. It's easier with numbers. I think that's what I wanted to do over here. I think an expression for the maximum speed is little v equals, well, come back to it, Mr. Dueck. I'm still blanking. Thought I had it for a second there. Gosh. Recover, Mr. Dueck, recover. Current and direction. Well, current is V over R. I guess it's going to be 320 divided by 8.5. $37.6. Direction. That way, clockwise. Yes? What's the current here? Bigger or smaller? It's going to be a little smaller. Because why? Because our net voltage is going to be a little smaller. 308.5 divided by 8.5. You guys can use your exact values. 0.35 times 4.1 times 8. And then I go 320 minus that. And then I go divide by 8.5. You get 36.3?
Yeah.
And then is D asking me to find the force, I hope? And magnetic force on a wire is Bill. Oh, direction. Still the same direction because the main battery is still winning, right? And it will always be in that direction, or the magic number, when there's no current at all, when your EMF induced is 320, then your net current is 0. Well, then there's no direction. Right? Bill, what was the 0.35? Here, 37.6, 4.1. And here, Bill, 0.35, 36.3, 4.1. You get 54 newtons in the left-hand one, and in the right-hand one, 52.1 newtons. So is there still a net force? Yep. Is it still accelerating? Yep. Is it accelerating more or less or the same as a few moments ago? A little less, because F equals ma. M didn't change. What must have changed? A. That's the only way you can get a smaller force. Oh, direction? In each of them, because the current is still going this way, you still have more charges moving down than moving up. So your net current is still down, magnetic field into the page, still accelerating. Is that okay? So to the right, to the right. What's your homework? First, you're going to get a take-home quiz on last unit. That's your first bit of homework. Then, although these are really cool, oh yeah, comic, okay. So what's your homework? And then from pause for a second. You can already do number 1, number 4, 6, 8, 18, 20, 30. I like number 30. I like number 30. I like number 30. Number 30 is a nice question. $35. $43. And let me give you the take-home quiz.